A planet that should not exist drifts on the edge of physics, challenging every rule we rely on. In this video, we pull back the curtain on exoplanets that seem to bend gravity, atmospheres, and orbits, and we show how real data turns science fiction into testable theory. You'll meet the candidates, unpack the evidence, and see how researchers separate dazzling possibilities from honest doubt. By the end, you'll understand why these extremes matter for how we study the cosmos and what they could teach us about life beyond Earth. If you crave ideas that push the boundaries of what's possible, you're in the right place. Planets that defy physics. Concept. Exoplanets have stretched the boundaries of planetary physics by occupying regimes once thought unfathomable. Some circle their stars in blistering proximity. Others drift through interstellar space as rogue planets, unbound by any stellar warmth, forcing us to rethink thermal budgets, climate, and even the definition of a planet. These extremes frame a concept researchers call planets that defy physics. The core idea is to study real worlds that push our models to their edge, where irradiation, tides, composition, and energy transport collide in surprising ways. Pulsar planets orbit neutron stars and endure radiation, gravity, and magnetic fields that would annihilate simpler worlds, yet several are known to persist. Their very existence tests formation pathways after stellar death. In contrast, hot Jupiters such as those locking themselves close to their host stars exhibit intense heating that inflates their atmospheres and, in some cases, drives atmospheric escape. This atmospheric loss is detectable through signatures in ultraviolet and Lyman alpha observations. The case of a planet losing mass to Roche lobe overflow shows how a world can survive while shedding material, effectively blurring the line between planet and star in extreme conditions. WASP-12b is often cited as a dramatic example of this process. Microlensing surveys hint at a population of rogue planets roaming the galaxy, free from starlight, and demanding new intuitions about energy budgets, detection, and atmosphere. Direct observations of such planets are challenging. Similarly, planets detected around pulsars present a paradox of unusually resilient bodies in a milieu shaped by supernova remnants and strong magnetic fields, suggesting either resilient formation or second-generation creation. The diversity of densities, compositions, and orbital architectures among known exoplanets continues to surprise. Inflated radii in some close-in planets point to ongoing internal heating, tidal effects, and unusual atmospheric dynamics that standard models must accommodate. In all these cases, physics is not broken, just pushed to the limit. Framing the concept this way helps guide observation strategies, because extreme cases highlight which physics knobs matter most for planet structure and evolution. Transit spectroscopy, precise radial velocity measurements, and gravitational microlensing are the chief tools. As instrumentation improves, we will better constrain which worlds truly challenge our expectations and which explanations, like tidal heating, atmospheric escape, and non-solar compositions, fit the data. The idea remains a practical one. Exoplanets that seem to defy physics illuminate the limits of current theories and point the way to deeper understanding. Observational methods for exoplanets. Observational methods for exoplanets rely on the planet's influence on its star or on the light the planet emits or filters, and these methods map out a diverse toolkit. The main approaches include transit photometry, radial velocity measurements, direct imaging, gravitational microlensing, and astrometry. Transit photometry watches for tiny dips in starlight as a planet crosses the star's disk, while radial velocity tracks the star's Doppler shifts as the star wobbles under the planet's gravitational pull. Direct imaging captures photons emitted or reflected by the planet itself, often with sophisticated optics that dampen the glare of the host star. Microlensing leverages gravity to magnify a background star when a planet-star system passes in front of it, and astrometry records minute shifts in the star's position caused by orbiting companions. Each method has its own niche, sensitive to different planet sizes, orbital separations, and system distances, and they often complement one another to build a coherent physical picture. In practice, discoveries are strengthened when multiple techniques corroborate a signal, converting a detection into a robust set of planetary parameters. Transit observations deliver a direct measurement of a planet's radius relative to its star because the depth scales with the area ratio, and repeated transits reveal the orbital period with high confidence. This method also enables atmospheric studies through transmission spectroscopy, where starlight filtering through a planet's atmosphere during transit carries imprints of chemical species. Signals from water vapor, sodium, and other molecules have been detected in the atmospheres of several well-studied transiting worlds, illustrating how atmospheric composition can be probed from afar. The technique shines for planets around relatively bright stars, where high signal quality allows precise measurements of both radius and atmospheric signatures. TESS finds many nearby, bright examples that serve as excellent laboratories for follow-up with ground-based facilities and space telescopes, expanding the catalog of transiting planets with measurable atmospheres. The method, however, is most effective for short to moderate orbital periods, where transits occur with regular cadence. Radial velocity measurements reveal planets by the star's motion along our line of sight, induced by the planet's gravity. High-precision spectrographs quantify tiny shifts in spectral lines, translating them into a stellar velocity curve from which the planet's minimum mass is inferred. The strength and shape of the wobble depend on the planet's mass and the orbital geometry, and combining RV data with transit measurements removes the inclination ambiguity to yield a true mass and, consequently, the planet's density. This synergy has dried a lot of the ambiguity surrounding worlds that are difficult to characterize by brightness alone, especially those that do not transit. In nearby stellar systems, radial velocity campaigns have revealed multi-planet configurations, including series of super-Earths and Neptune-like bodies, illustrating the method's ongoing power to map planetary systems in detail. The precision of modern instruments makes it possible to detect ever smaller companions, pushing the boundary toward Earth-sized planets in favorable circumstances, though stellar activity can complicate the signal and requires careful modeling. Direct imaging, microlensing, and astrometry broaden the observational horizon in complementary ways. Direct imaging excels for young, massive planets on wide orbits, where the planet shines against the star's glare, and high-contrast imaging systems like advanced coronagraphs enable photon-by-photon separation. Notable systems with multiple directly imaged planets demonstrate the method's strength in studying atmospheric properties and orbital dynamics in a self-contained package. Gravitational microlensing probes a different regime altogether, capable of discovering planets at several astronomical units around distant stars, including cases where the lensing geometry makes the planet's mass and separation accessible even without a light signal from the planet itself. Astrometry, refined by precise measurements of stellar positions, provides direct access to true masses and orbital configurations without the sin-eye degeneracy that can affect radial velocity. Gaia-like astrometric programs are mapping a vast population of planetary systems, informing theories of planet formation and migration on a statistical basis. Together, these approaches create a multidimensional view of exoplanets, from hot Jupiters to cold ice giants, and they offer vital checks against spurious detections. Within the frame of the planet that shouldn't exist, observational methods act as a rigorous sieve for truly extraordinary candidates. If a signal suggests an unusual orbit, extreme mass, or atypical atmospheric physics, cross-checks across different techniques help separate genuine anomalies from instrumental quirks or data artifacts. By combining transit timing variations with radial velocities, or by pairing direct imaging with astrometry, researchers can test whether an ostensibly paradoxical world stands up to independent scrutiny. In practice, the strongest cases emerge when multiple lines of evidence converge, offering coherent masses, radii, and atmospheric fingerprints that can be explained within physics or, if necessary, motivate new theoretical work to revise our understanding. This collaborative, method-by-method verification keeps the field grounded while still leaving room for genuine surprises that challenge preconceptions about planets and their possible laws of behavior. Anomalous candidates and their challenges. Exoplanets with properties that strain our current physics exist in the catalog, and they invite careful study rather than quick dismissal. KLT9b is a hot Jupiter. It orbits an A-type star so closely that dayside temperatures reach into the thousands of Kelvin, pushing models of atmospheres and mass loss to their limits. Atmospheric escape is a real feature here. WASP-12b expands the list with an inflated radius, nearly twice Jupiter's in some estimates, and signs of tidal interaction that may siphon material from the planet. The result is a planet whose outer layers feel the star's gravity more than its own. HD 106906b occupies a very wide orbit at hundreds of astronomical units from a binary star, a configuration that challenges how planets can form and yet remain bound. Its existence points to dynamical histories that theories must accommodate. Pulsar planets, such as those around PSR B1257+12 defy simple timelines for planet formation because they appear around the remnant of a supernova. They force questions about where material comes from. Rogue planets drifting through interstellar space, detected by microlensing, show that planets can exist without a star's gravity to anchor them. This expands the category beyond conventional planetary systems. WASP-17b demonstrates that migration can tilt a planet's orbital plane, producing a retrograde orbit that challenges smooth disk migration pictures. The mechanism may involve gravitational interactions with other companions. GJ436b, a Neptune-mass world in a tight orbit around a cold star, retains a measurable eccentricity that runs counter to the expectation of rapid tidal circularization. These are clues rather than conclusions. Many anomalies survive only as signals in messy datasets, not as settled planets. Stellar activity can mimic transits. Blending from unresolved binaries and instrumental systematics can masquerade as shallow dips, requiring careful vetting and follow-up. Radial velocity measurements help, but require precise mass estimates and stable stars. The process of confirmation often reveals more about the star and the data pipeline than about a lone planet. False positives are a natural part of frontier discovery. In this light, anomalous candidates become guides to better measurement and better models rather than stubborn contradictions. To resolve these anomalies, astronomers combine transit data, high-resolution spectroscopy, astrometry, and dynamical modeling. The goal is robustly measuring masses, radii, and orbital configurations. Upcoming facilities and missions will sharpen atmospheric chemistry, detect escape signatures, and test migration histories under more realistic physics. HD 106906b and similar wide separation planets will become laboratories for formation channels beyond core accretion. KLT9b and WASP-12b provoke detailed studies of heat-driven expansion, metal atmospheres, and the end states of tidal locking. The chorus of anomalies thus helps refine theories instead of breaking them. Theoretical explanations and skepticism. Exoplanets are detected through several methods, with transits revealing subtle dips in starlight and radial velocity measurements tracking wobbles in a star's motion. Some signals hint at properties that would bend our expectations. A planet that seems to violate common physics is not accepted as fact until independent confirmation arrives. The phrase "planet that shouldn't exist" works as a provocative way to describe signals that tempt us to rethink something fundamental, but the correct response is to test thoroughly. Often, what looks exotic turns out to be a combination of measurement bias, stellar behavior, or simple misinterpretation. In the end, physics remains a guide, not a prison, and the universe frequently teaches humility. Theoretical explanations for such odd signals cover inflation, composition, and dynamics. One category is that planetary radii and densities inferred from light curves and velocity data may be biased by how large the star really is. Stellar properties matter. If the host star is enlarged by activity or misestimated in size, the derived planetary radius inflates, and the calculated density may seem impossible. Two common physical explanations for unexpectedly large radii involve intense stellar irradiation and internal heating that slows contraction. Inflation happens. Mechanisms like ohmic heating or tidal dissipation can pump energy into the planet, puffing it up beyond simple models. Atmospheric escape and extreme irradiation can also alter the planet's apparent density when we interpret transit depths against models of composition. Conversely, extremely dense planets invite debate about their interiors or history. sometimes prompting the diamond planet hypothesis. That idea has evolved with better data and modeling. Analyses often show that high density can be consistent with rocky or iron-rich compositions if mass is well constrained, but atmosphere may still be thin or absent. Skepticism in this area relies on cross-checks. False positives are a known risk. Transit signals are vulnerable to background eclipsing binaries. A distant binary star along the line of sight can imitate a shallow planetary transit. Radial velocity measurements must rule out stellar companions. Multi-method confirmation helps. Direct imaging and astrometric data from missions like Gaia help determine whether the host star is mischaracterized, which would skew the inferred planet's mass and radius. Independent teams replicate analyses. Statistical validation can classify a signal as likely planetary without a full mass measurement, but skepticism remains until a mass is measured. The case of claims about extreme properties is a favorite proving ground for improving models of stars, planets, and the observational processes that connect them. Practical approaches to these questions include improving stellar characterization, combining datasets, and using population studies. The tools for this are diverse. Advances in astroseismology, high-resolution imaging, and long baseline astrometry sharpen mass and radius estimates, reducing spurious extremes. Upcoming and current facilities monitor stars with greater precision, enabling tighter constraints on planetary densities and internal structures. That helps separate real outliers from artifacts. Even when signals push the edge of known physics, the prudent stance is to test, revise, and seek confirmation. The aim is to build a robust picture where apparent violations of physics either reveal new science or dissolve into measurement realities. Implications for science and future research. Exoplanets occupy a wide range of environments, from scorching gas giants that bathe in ultraviolet light to compact super-Earths that bend the dynamics of their stellar neighborhoods. And this diversity already stretches our current theories in meaningful ways. Some instances look almost paradoxical. The planet that shouldn't exist, and the Russian tag of Exoplanet, Narushaishik Physические Zakona, captures a tension between observation and expectation that science uses to calibrate its models. No planet has overturned physics yet several real worlds hint at edge cases where formation, migration, and survival depend on extreme tides, strong stellar radiation, or unusual compositions. Hot Jupiters, circumbinary planets, and rogue bodies illustrate the spectrum. Hot Jupiters like 51 Pegasi b revealed that nothing about a planet's birth guarantees a quiet orbit far from its star. Their existence reshapes theories of planet formation. WASP 12b shows tidal forces so intense that the planet may be losing mass to its star, a process that informs atmospheric escape and Roche-Lobe dynamics. HD 80606 B has an eccentric orbit that swings the planet into extreme heat and cold. Kepler 16b demonstrates that stable planets can orbit two stars, a configuration that broadens the possible architectures of planetary systems and tests disk-driven migration. Rogue planets discovered by microlensing hint at planets roaming the galaxy without a sun. If such extremes persist in observations, physics departments and astronomy teams must unify gravity, fluid dynamics, and atmospheric chemistry to reinterpret data across wavelengths. That means refining mass-radius relationships. Atmospheric models will need to handle runaway escape, high-energy irradiation, and non-Earth-like chemistry when predicting spectra. Migration theories will be stress-tested. The possibility of misinterpreting signals due to star spots, stellar activity, or instrumental systematics becomes a central concern that drives better calibration and independent verification. Multiple detection methods must converge. Upcoming and current facilities, from JWST to ground-based extremely large telescopes, will push atmospheric characterization into new regimes and help distinguish true anomalies from artifacts. Microlensing surveys will illuminate the population of rogue planets. Combining transit, radial velocity, astrometry, and direct imaging in unified pipelines will sharpen mass and radius estimates and reveal subtle signatures of unusual compositions. Population studies will map out what counts as a weird planet and why. The research questions will shift toward leveraging edge cases to test physics in regimes previously inaccessible. guiding the next generation of simulations, laboratory experiments, and cross-disciplinary collaboration. Ultimately, even if no planet truly defies the laws of physics, the exercise reveals gaps and opportunities that push science forward. Tonight's journey through the planet that shouldn't exist reminds us that exoplanets can feel paradoxical, but usually the answers come from better data and deeper physics, not from bending the rules of the universe. Key takeaways. Anomalies in exoplanet observations push our models, but many apparent violations stem from measurement limits, stellar activity, or complex gravitational dances. When an odd world stands up to scrutiny, scientists refine theories and improve methods rather than abandon physics. And in the end, these strange worlds illuminate new regimes where known physics still applies in surprising ways. If you watch to the end, you're the kind of viewer who loves wrestling with big questions. First, I'd love to hear which world you found most mind-bending and what topic you want us to unpack next. Share your thoughts or questions in the comments, and tell a friend who loves space puzzles to join the discussion. If you enjoyed this dive, hit like, subscribe, and ring the bell so you don't miss our next exploration into the strange side of exoplanets. We've got more on the way. Stories about how atmospheric spectra are interpreted, how teams separate signal from noise, and what future missions might reveal about worlds that push the boundaries of physics. Up ahead, we'll pull back the curtain on how JWST and other observatories reveal exotic atmospheres, and we'll peek at upcoming missions that could uncover even more impossible planets.